So this week we continue with the tutorials that we started last week, and it's a pleasure to have John Liu with us. So he's gonna give us a tutorial on today on asymptotic-preserving schemes. So
thank you very much. It is my great pleasure to share with you some of my thoughts on the subject. Asymptotic-preserving scheme for fluid and kinetic equation. I learned most of the material from my collaborator, and particularly Pierre Degan, Xu Jing, and Luc Musin, and which is basically they control really the ideas. All right, the precise fluid and kinetic equation I mainly emphasize on asymptotic preserving. So it is more regarded as a numerical analysis question. So for the general methodology of questions which have a lot of discussing, and it can be, I refer you to look at the great work by called HMM by Wen-Yi and Enquist. So I will probably today will most emphasize on some of simple numerical questions rising on these issues. Basically means how the efficiency, consistency, stability, and more importantly, what it means asymptotic preserving. And there's some small numerical tricks which will be issues be some useful. That's what I would say. So let me just begin, just outline a few questions which are going to be emphasized. Maybe I can stick in here. So I guess doing this asymptotic preserving scheme involves small parameter, and some of small parameter is something important, something not important. And something not important, I want to under-resolve. So basically, like fast waves, small mean-free paths, and background scattering, and which you do not want to resolve in every detail, which is not possible. So the way to do that is how to do this one is basically control either two main things. One is the time stepping resolution issue, which you like to under-resolve, which means you take a bigger step, not to cat details. The first thing. Secondly, more importantly, is the truncation area control. So you can have this truncation area 1 over epsilon, large terms here. You do time disposition and involve larger terms. And this large term, where to put? You cannot avoid this large area. And this area had to be controlled in some way, in particular in Aurelian framework, like fluid equation, kinetic equation in Aurelian framework. Then this becomes really important. And how to control this truncation, which I'm going to probably may emphasize. Then some techniques, just general techniques, sort of called a predicted correction, or called a micro-local precondition. I'll give you say little more details, and how to do the localization if when some problems need. Okay, so let me just use this marvelous diagram by Xu Jing, what he said. So here's a sort of cartoon picture what the problem like to work with. So you have the physical problem, involves small parameter epsilon, can be mean-free path or like a Mach number, and you have the grid size discretization, H, whatever you like, find difference, find whatever your favorite. So now you will see you are leading to the leading behavior itself, of course, the solution at epsilon to 0, and this like the incompressed flow or fluid equation. That's what leading to. So traditionally we do this way, okay? So the double limit is take h equal to 0, you get this guy, then there's this 0, of course you can do it. That's why you prove anything like it by trivial, because then you have the h will be far smaller than epsilon, and it's almost impossible. It's impossible because epsilon is small and equally size small. So this passing is unrealistic. You can do it, but if you have all the power. But now what the other direction will be suggested. So what I like to say is that build up this guy, you do asymptotics in that continuous level, you do asymptotics on discrete level. So it means you should this dynamic system for the discrete system itself should share same behavior as continuous. If you formulate it right, that's what require some thinking to reform problem such that make the calculations itself. You have to perform asymptotic analysis in this discrete setting. So if you do this one, that means this guy, you want to have this guy uniformly in two things: uniformly stability. Uniformly perform the asymptotic preserving. At the same time, you want to uniformly accurate. So that is a new concept involved, asymptotic. Just as usual, stability, consistent, efficiency we'll talk about, but more importantly involved uniformly stability, and more importantly uniformly in accuracy, consistent. That means you should be, the limit equation should be preserved. So this will be able to pass limit itself to the. That is the program was Xijing will be first started with. By the way, I will refer to whatever I know. Maybe literature is I not completely know all the details. So maybe I omit some of important work. I ask you for excuse. Okay. So now that's just the picture. So now here I will say a little more details. So what AP means. So you're doing kind of this kind of a problem itself. I'm more looking at the dynamic problem itself. And dynamic problem itself, of course, the older understanding is let's take implicit, everything make implicit, then it's going to work stable. That's true, certainly true. But implicit work, what's the implicit means? Implicit means introduce a lot of numeric dissipation. It's 1 over epsilon. It's completely destroys behavior. So you cannot do that. Although you can run the computer, but you will get not necessarily right solution. So really what we will try to look at AP strategies is tell you exactly which terms you can take implicit, which then you will try to minimum possible implicit terms, such that you have to get the right behavior. So that's what we like to do for the efficiency, for stability, and also remove the numeric dissipation. Okay, and also many of the schemes itself, you like to have stability, so formally it's implicit. I'll give you more examples, you will see digest what it means. But actually important, if when your realization itself is completely explicit realization, that will be efficiency means here. Okay, now here this part I want to be digest in more detail. So numeric dissipation has to be controlled in leading variable. Let me just say. So we have, as we know, parameter 1 over epsilon factor of truncation area. Because to tell expansion, you have truncation area. And this kind of truncation area has to be stable. So in this case, we call it numeric dissipation, right? Because this large area, but it's good way, more stabilized. So we call it numeric dissipation. But this kind of only appears in the unimportant variable, or in orthogonal space to the leading variable. So this unimportant variable, for example, I'm going to explain like the compressor flow. And if your density itself is small fluctuation, and if you put many for the numeric dissipation, it doesn't matter because it's constant anyway. So you put any numeric dissipation in there will not affect your own computation. So that's where you're able to put this large area in the location where it can be ordered. And another for the solving for like a kinetic equation itself, then you will have leading moments and higher moments. You put any numeric dissipation, higher moments doesn't matter because you can project anyway in the leading behavior. So that's why you want to put any numeric dissipation orthogonal to the leading variable. So that's the way control. And if we have the good consistent analysis, then it's always leading to this good stability. So the more important to look at the consistent, then look at the stability. Stability as byproduct if we care for doing the consistent analysis. That's what I think. Okay, so then other way of problem itself will try to do something is reduce in the singular perturbation, try to see in numerical formula in a more regular perturbation way. Just instead of doing the fast wave, we see doing some sort of in a more solve global equation, like in more. I can say some examples. You try to make my points more clear. Okay, so that's sort of. I always would say this kind of computation method called a preconditional. So that means you follow the leading dynamic, make a necessary correction or predicate correction for the. Then you to under resolve some details which you don't need. So that is it. So let me just begin with some equation to illustrate the idea. So for the Euler-Poisson equation, okay, that's the mainly this idea really comes from Pierre Degas, and as I said, all the idea come from my collaborators. Okay, so so that's the work. So let me just try to first just explain a little bit clear. So beginning with scalar equation. So I do not do the dimensional analysis. Just beginning with scaling behavior. And there's two charges, and you want to be close enough. Have this the balance to enforce it close enough epsilon. And this just is Euler equation with electric field to acting on the the force. I use the Q variable as the momentum and the density, or number density is charge. Okay, so this one. And formally, you will always look at two things. What is the formal limiter? What is fast waves, right? Formally take epsilon equal to 0. This guy is 0 and the density equal to 1. And you plug in, and this is density 1. Remove out is just the incompressible Euler equation. So that's the equilibrium behavior. That's idea come from Young, right? I guess. Okay. So that's the equilibrium. So now also we would like to see this. What is this? This called plasma frequency behaviors. So you just look at this density variation. You just linearize along the base background. The velocity is 0 and s is 1. You do asymptotic slow Hamilton and reduce to very simple Gaussian equation, with the 1 over epsilon square here come from this the balance. And now for this Gaussian equation, of course, you take a distribution relation for traveling wave. Just simply a normal mouse, you plug in, say speed is you will go very fast, 1 over epsilon square. So that is Klein-Gaussian equation underlines. Basically, was Euler-Poisson is basically incompressible Euler equation plus Gaussian equation, and scattering background waves. So you want to build up this mechanism numerically, see how we can catch up this behavior. Okay, so I guess explain the first write down scheme, then I try to explain how it works. Okay, so here is just D. I did not do not say anything D. Any kind of time spatial disposition like Apollinean scheme, shock capturing scheme is going to work. And just this part is just regard as usual shock capturing scheme. Only difference, main difference here, Q is very important. This variable has to be n plus 1. If we mess up this one, will be dead. At least like numerically will show that. And also simple analysis will show this. Okay. So now this guy is right hand side equal to this guy. And then this you have just usual disposition. Okay. So now this formula looks like a complete couple, right? You have n plus 1, n plus 1, n plus 1. So, but there's a way indeed you solve this one. Look more careful. Solve this question indeed is explicitly. Besides this one, you have solved 1% equation will be enough. I'm going to expand. So, so that's just notation. I put all this sort of terms like this initial force and this pressure force. This guy is in non-Newton and this variable, because I do this one because anything what's not important is use time previous time step, which I lead in. N get n plus 1. I didn't know I put this all lumping here. That doesn't matter in computational. Okay, so and so if we like to do like a more careful shock calculation, we're doing the this Apollinean scheme and this implicit scheme. But I want to expand explicit realization. Only 1 Poisson equation per time step. It's quite efficient. It's almost efficient as the explicit scheme. It's the best I can hope. And this is we did some analysis for the linearized. Okay, by the way, any kind of numerical analysis for this kind of problem is very limited. You will not like see fancy original equation. We're just only doing simple one like linearized equation or some Euler-Poisson equation for a simple problem. You can do that. Okay, so let's just try to see this Degan's great idea, and of course, it may probably originate from Young, I guess. As basically they solve this kind of global equation, what we know, some physical system at a limiter is always become more singular, more global, like incompressible. It's background scattering field out. So you will solve this problem of what's the best method to solving incompressible global, and it is called pressure Poisson equation. That means how to realize divergence free as a Lagrange multiple in an effective way. Okay, so let's just look at this quasi-neutral limiter, or just with incompressible Euler equation, and solve the equations of mainly try to choose the pressure or like the electric potential as the Lagrange multiple to enforce divergence Q equal to 0, or you solve this pressure Poisson equation. So that's the main leading method to solve this incompressible, the leading dynamic. You have to really follow exactly this method, because as we said, we would like to solve. I do not have it here. So we would like to solve this question as this preconditional. So this linear dynamic make a correction and solve this one. So the sort of predict the correction. So that's you should follow the what is the linear dynamic do. So that's what the linear dynamic do. So now how to formulate this problem itself in the way very close enough to this guy, and this variable itself will manipulate with this equation. I will not show you, and I'll refer you to read the original paper. So you just solve this equation itself with this elliptic equation, like the analog. If the density is 1, and this guy involves some time derivative, but it can be time lagged. You can solve this guy, and then you will see solve this equation. So basically, the same course as this one. I'm going to see more numerically, see how to realize. So if you do this one, then you regard this singular perturbation problem become regular perturbation problem, originated from young early time. Okay, so now let me just try to see how this turns out in discrete setting. So if you manipulate with the equation we have, let's just do just usual way. So this guy cancel this middle term. It's doing time difference here, and take the divergence here, and just subtract it, become the signal wave equation. And you eliminate this guy, and then become this guy terms here, and use this relation. Then you will have this simply calculations. That's what the main calculation have. So you now have the pressure Poisson equation for this one, and this time lag will be put here, and this term. So your first step is to solve this phi pressure Poisson equation, and that's the main computation you have. Once you have this one, you have this variable. Then you can looking back to this original problem itself. This guy, you know this value. You solve this one. And can solve for here, Q. It's that just explicitly. When you solve this guy, and you know this guy, you solve this one. It's, the cost is really limited. So you really have to compute extremely efficient. So it's, I always talked with Xi Jing, and he always have implicit explicitly realized. So that's for IP skin, always try to looking for this kind of efficiency. Okay. All right. So now then also is about this the truncation area, consistent area. So you look at the fast waves. You just I just look at linearize problem because that's behavior is scattering is really linear behavior. If you look at this numerical scheme itself, you look at the scheme itself, you basically will see exactly this Klein-Gordon equation in a good disposition. So you just this one does not involve fast variable. Just usually central difference will be good for the leap forward. So that's just the usual central difference. But then this guy Klein-Gordon terms therefore m plus 1. But this guy gives you a large error because this is not m. It's really m plus 1. So it's involve the 1 over epsilon n. But this one only affects on this density variable. It will not affect on u variable. That's okay. You don't, density is it's also this guy is this truncation area is in the good side. That means it's a stable manner. We call it numerical dispersion. You just basically just make the density more smooth. It's over smooth, over damped for density variable, but it's not so important. If you really want to know details of density, then other issue. But then you have to require the numerical resolution. Okay, so that's for this one. All right. So now, how far we can do? So we like to this would be simple baby model. Working all the Poisson equation, and of course, you involve the more complex equation can be fully Navier-Stokes equation. You're working on the Navier-Stokes Poisson equation, and then also involve the sort of localization, some of all speed, some Mach number from small to large, all the range itself. So we like to ideally like to have the all speed. And the way to do that is there's a different approach. I'm going to say two approaches. One approach which based on method called Hughes decomposition, called gauging method, which is have some relation with my early work with W9E on the incompressible flow. Okay, so let me try to basically try to follow the idea for how to compute the incompressible flow. We know compute incompressible is difficult. Yeah.
So I have a question about the previous slide.
Yeah, sure.
Because, I mean, for the elliptic equation,
Yes.
you have to solve an equation with coefficient rho n, right?
Oh yeah. Well, linearized. Did I say?
Can
Yes. Yeah, yes.
From the theoretical point of view, can you get some lower bound, to control the ellipticity of this equation? So because, if rho n is,
You mean?
has very large values or very small values.
Yeah, vacuum place, yeah.
Yeah.
Well, yeah, because on this region doesn't matter because this is close to equilibrium, like a 1. Because
But so you can get some estimates on that?
No, I just this is for this no. Of course, if we can estimate any kind more show this really convergence to the some analysis. But now this now I haven't thought about this question. I probably mainly try to look at the problem itself. So far is close to the 1 enough, so it will not give you the issue on coercivity. But no, I do not have the good sense. Yeah. Maybe I should look into And for now, this problem, I really try to treat the other numerical analysis, purely numerical, say which giving good numerics, which giving bad numerics. But I'll talk about analysis later. Okay, so let me just back to the gauge method. So what the idea we learn from incompressible. Incompressible if strictly enforce incompressible two region. So there's the idea is try to make it relax. We like the pseudo compressibility method, which like let sportsman expert was sitting back. So as was basically the same idea. Anything we try to choose the method itself which is in good manner to handle it. So that's I will be more and this problem itself we could all speed is important. Like for example, air bubble in the water in plus the bubble itself then is not uniform in speed. So it's sort of quite involved. Let me just share with the idea with the okay again this is still this I just explained my early work with Weinan. Of course, all the great idea I learned from incompressible from Weinan. Okay, so let me just maybe quickly try to tell you how the gauge method means. The mechanic. So this Navier-Stokes expression, I instead of look at U and P variable, introduce some variable A, arbitrary, some freedom, and a hope for freedom will give you some good sense. That's for the gauge freedom. Just learn from like the electromagnetism, more close to Coulomb gauge. So you artificially choose these two variables, make it relax. You plug in U into this equation itself, you write down this momentum equation in this form, and lumping all computations in here. And hopefully we choose some gauge such that this complication becomes 0. Then it will be more efficient in the numerical method. So luckily for a very simple problem, of course, this guy will be asked this incompressible. Kinematically, this will be very divergence get this guy as fine. So now, what we in the 97 indeed there was time we will look at the Turing's idea on this called impulse density variable formulation, and more geometrical way. And we found that the system will be marginally well posed or weakly near posed. Basically, the system with the Turing worked on this impulse variable, you have Jordan block, so which is the numerical shoes oscillation, and indeed doing simple Fourier analysis, see this indeed is the near posed system. So with we will try to improve what Turing has on this impulse variable formation. That's what we come up with the idea. And then we realize this indeed the idea for incompressible is that when you treating viscosity implicitly, and the complication comes from boundary. And this was needed to play with the boundary itself. So the idea was over there at that time, in 97, what Weinan and I, we had is sort of just impose some kind of, because he introduced this another derivative have freedoms, the actual condition to play with. You just play this addition, this degree freedom put on boundary, and impose this boundary condition, then turn out this exactly, or because this boundary condition will cancel this guy. It will impose this guy 0. It will exactly by impose this boundary condition. So this gauge freedom will impose on boundary. And once you impose this boundary condition itself, then we have very simple numerical method. Okay, this sort of numerical method itself, just sort of, because now the complication is 0, it's just simply convection diffusion, and with boundary condition, and then to kinematic. But anything was originally coupled together. But then you will simply just do time lag. Instead of this n plus 1 here to the n. And then the time lag. So now this is completely coupled. You just solve this equation completely separate, extremely efficient, like a projection method. And this indeed is numerically extremely stable. It's unconditional stable. Indeed, we proved with my former students some years later, we proved this indeed method is for Stokes problem is unconditional stable. So that means tell you that so not only introduces good gauge to take a complication on pressure, at the same time, it doing decouple system itself is unconditionally stable. And this could be useful for AP. That's what we like to follow the idea to handle here. Okay. Yeah.
The Stokes equation, you mean that nu equals 0, right?
No, Stokes is a nu equal to infinity. Zero. So means I means take the non-linear term out.
Ah, okay.
Yeah.
Because it's still appearing in this.
Oh yeah. But this here, because that means in this case itself. This is for non-linear problem. I say all the numerical analysis has to be in ideal situation. And if we cannot do it, we can make assumption. And the non-linear we cannot do it, we just say work on Stokes problem. I just take this away. So that's what I mean. Okay, I'm sorry, because I don't know this is the way to be make efficient. And also, I really think this issue is really for the linear problem, not the non-linear problem. It's really because it treated explicitly, really like the linear system is probably carry more behavior than non-linear problem. Oh yeah, that's right. I'm sorry about slides because I put both in there. Yeah. Okay. All right. So now let's just back to the how to follow this idea to work on this fluid equation. Okay. So we just again just scatter Navier-Stokes equation. Begin with asymptotic. So that's this nice is because this is the dilational invariant. That's what it's scaling invariant. That's what's how powerful it is. But then, of course, subject to this Mach number because only involved is Mach number. Of course, another Reynolds number we will not talk about. And by the way, so I try to explain things here is treat this viscosity explicitly from now on and to avoid complications. Because in practice, this high Reynolds number is okay, and if as long as you treat this explicitly, then it's nothing more different than the Euler equation. So that's what the easy to do. If we really insist on implicit, then will be complication coming. But I don't want to say much in here. Okay, so that's just usual, and with viscosity, of course, impose boundary condition, and it's just usual asymptotics explained to you. Okay, yeah. First of all, important here is epsilon. What epsilon means? Epsilon square. Mach number, of course, usually depends on the speed compared with speed of sound. But more importantly, to my regard, I will regard as more important is the speed of sound is a square regarding the ratio between kinetic energy and internal energy. When you look at the fluid equation itself, we always try to see how much energy transfer from momentum equation to the internal energy. And if this layer large or small, depending on how you say, and it's so rich that there is no transfer between momentum equation, kinetic equation, and to internal energy, that is asymptotic will be enough. And that's also impose density y is kind of 1. So, that is, I can explain more when I'm doing full Euler equation. Okay, so now again, look at this guy itself. So the hydrodynamic pressure itself is a perturbation. This thermodynamic pressure we call, and this is more perturbative pressure, or called hydrodynamic pressure. And again, you solve this equation, always the leading term has to be solved with pressure per zone. Otherwise, you will not get AP. So we certainly will define this one. So now let's just how to formulation this gauge formulation. A little bit complicated, but let me explain. Okay, so again, we this Q or U because I will involved. So introduce this A and Phi variable as usual to freedom and make the divergence free. So now then momentum can become this guy, but now this guy cannot. This time it cannot take it out. Choose the gauge or to the slot away. But we have sort of way to update in a good way. So we choose this P variable as an object constant. So some normalization constant doesn't matter. So P will be subtracted this background constant divided by epsilon square plus some phi t. So if we have sort of time evolution to pick up this guy, then we have good way to do that. So that's what introduces potential. Okay, so now this potential itself is a computer quite effective because this potential is really try to see this perturbation in density, and this Laplace P is in time derivative phi t. So it's really like the time variation of density. And so then we would like to, in this case, if we introduce, then we just simply have very nice, this P is at a pressure per zone as income. So this becomes regular perturbation. So that was at least give you have mechanism to be stable here. And then of course boundary is complication. I will skip this guy. So now here's the formulation. We call the gauge formulation. Okay, so now, the equations of, as we said, now they have incompressed flow and also fast waves. So in this case, the fast wave, like just this fast wave, problems of scattering background. And this guy is the fast wave itself. First of all, the terms like this one, you want to solve this one in a under-resolve, in a stable manner, which just solve the one Poisson equation. Okay, so you have to solve this guy. And once solve this density itself, then you can you have time derivative and get a phi variable, and solve this pressure Poisson plug-in and get increments the leading behavior. So this is indeed the exact time step I'm going to explain in next slides. Shows how to update to the process to update in a stable manner. Okay, so this time sequence you have. So now if you let me just see a little bit more involved here. So this guy involves stiff one epsilon square, doesn't matter because this guy itself can be under resolved because put all this density numerical spin on density, which is eventually flat, close to 1. So then you have this guy, then if you solve this, as we said, from this density, from wave equation, solve this guy, then you have solve this artificial phi variable, updated time dynamic changing from density background. Then you get to solve Poisson equation, then solve this almost like incompressed flow. And this is quite stable. Okay, so that's the, I will skip some details, but this is the way how to formulate. Basically, what I like to see the AP scheme is really the way to look at the equation, reformulate the equation such that it's friendly, or means become singular perturbation from regular perturbation, and such that it is if able to do Taylor expansion, you do not worry about the larger area 1 over epsilon. If numerical dispersion, you just in the way in the quantity which is you do not worry about, like the density be flattened density. So it's okay because as long as you're not resolving. Okay, so now let me just try to say a little bit more involved, called the fully Euler Poisson equation. Now this time, Young's question the important density variation. Okay, and as we know, for incompressible flow, you can have large density variation, right? So really, to solve the problems of so where we get this incompressibility come from, that's really important here. It's not from density equation as usually in the illusion if density constant, then it becomes incompressible flow. But indeed, the more in this kind of larger density variation stuff, really the incompressibility comes from energy equation. Let me just this scatter. So this P is 1 over epsilon square after scaling. Okay, this internal energy is large. The real leisure have larger internal energy, it cannot move. So this is just the usual Euler equation stuff. This internal energy this is the energy equation momentum equation. If epsilon really large, this exchange is here so small. That's why we normally ignore energy equation. But some cases it's important. Okay, so here's just equation states the usual one. I choose the pleiotropic gas. I don't know if it's valid or not, but probably I just for now just choose pleiotropic gas. Okay, all right. So at the zero limit is incompressible, and then is density variation can be large. So now can we still catch up this behavior in a sort of gauge formulation? Let me just see. Okay, so now we have to be a little more careful because this time density is no longer constant. So you want to incompressibility, it's A like a momentum, and divide density become velocity. So this incompressibility comes from this guy. So we choose this. I'm sorry, it's in Q. It's not an A. Oh no, it's A. Oh, that's right. It's A. Yeah, that's right. Yeah, that's right. That's right. Yeah. So this is basically like a velocity. So, but in this case, you should be a little more careful on this guy. And the same thing. We cannot choose gauges to lumping P complete out. We cannot do that. Like incompressible, we're lucky we can take it out. But in this case, we again choose the time dynamic of this potential to lump into this peak here, and it's solvable, hopefully. Okay. So now then, of course, all the equation complication involved, as Young said, the density variation will have to be in there, and all the components is do small calculations. You show this pressure Poisson become this time here have the time 1 over density, this time variation involved here. And then use the important is how to get incompressibility. It's really from energy equation. Okay, so so how to see this? Let me just see clearly, because formally you can see that. Okay, you just take a time, make a reduced wave equation, take the one more time derivative for the energy equation. You have this just simply as in raw time, just as it's called entropy, right? Called H variable into here. And just put just time derivative this guy and time derivative this guy. Then you plug in this momentum equation, you get this sort of leading term like a sort of yeah, that's right. Yeah, so that's what gave the incomplete come from. So that then also once you have this one, then you have this sort of free value update. So let me just give you sort of a time sequence. The one. So a little bit like usual, because the energy equation itself is complete energy. So you can also use pressure. So it's just a time like wave equation update. I'm missing the green here. So wave equation. So this previous slide missing. Okay, sorry about it. This here is green here missing. So it's the wave equation. Okay. All right. So then you have time also minus sign. Okay. So then just say that this is basically sort of energy equation, shooting energy equation as sort of condition on divergence u equal to 0. So that's a little bit different. That's what is really energy equation in this case. It really means divergence u equal to 0. Then you're doing the density update. Then you're doing the usual. So that's the gauge formulation. Okay. So that's it's slides will be there. If you want to digest here. Okay. Okay, so let me move on to other formulation. By the way, I could keep a try, and I then know any method which work for everything, so different regime, and I just keep provide different kind of methodology, or hopefully some of will be useful. So, all right. So now next question is really like seems to me more fundamental, important here is you always. So what is how to solve signal nonlinear wave equation in good way. So indeed, this question first imposed to me by Stu Enterman when I just moved to Maryland like 10 years ago or something, 20 years, 10 years ago. And what he's asking the question, if we compute a rod, very nice incomplete rod itself, if fast spin itself, then how to do it? And usually for elastic problem itself, we like follow Lagrange. And Lagrange itself is a signal wave equation. Leading term up to leading term. So then you giving fast spin self. So you usual approach like we write down the signal wave equation, become first order system, then doing short capture scheme, introduce numerical expression, but it cannot come back because there's consistent error or continuation equation. So that's this one where we document quite some numerics to say the usual approach is bad because all the complications. So we do not have good solution for that problem. But for this problem itself, for some problem it's workable. We'll learn the idea from how much I'm doing okay? My time? Okay, yeah. So I learned the idea from this sort of complete connection idea, more close to Shelley Hall-Rulenberg ideas, marvelous ideas. So try to have stiffness, put the constant coefficients, then do it. So here sort of we'll take a sort of stiff part out and under resolving in a ways, which let me just try to explain some idea along this one, which work with Jing and his students. Okay, all right. So let me just begin again with Navier solution. Or you can disregard this part; it's not important. Okay. So you have a scalar with Mach number. I would like to uniform this Mach number. Of course, I limited this guy equation and sort of have nonlinear wave equation. Basically, have incompressible background at some scattering. That's what we have. Okay. So here is sort of the idea we call the hyperbolic decomposition. So as we know, luckily, all the physical system that we study is hyperbolic. That means stable. And for dynamic, to update dynamic problem itself, we don't have to follow exact physics. It's not so important. All the important is hyperbolicity. As long as hyperbolicity is dynamically stable, that's what we care about. So now we like to do is you kind of fake it. So instead of look at original physical system, I'll modify the original system such that I have good way to do that. But then the remaining system itself is still all you need just require is hyperbolic. As long as hyperbolic is stable and you can do dynamic. So that's the idea we'll explain. Okay. So you're doing this right-hand equation itself, you write a two component as a very simple one, we'll call it pre-conditional. So you put this nonlinear computation itself here is low dynamic. It does not involve stiffness. Can be nonlinear, you can do shock capturing, whatever you like. Then anything with involves stiffness part become linear constant coefficients, like the preconditional. So now let's just basically take this signal that we will operator out. So you do this decomposition. And the two subsystems itself, you have to be constructed such a way be hyperbolic. That means I solve this itself be stable. Okay. And this guy, Fu is a fully nonlinear. Nonlinear can be non-stiff. Can be the usual have a shock captain scheme kind of work, and this numeric expression. And this guy Q itself is a linear, and more important is the constant coefficients. So you have sort of the good way to solve it. Whatever you favorite method, you can solve this central difference. Other than linear problem, you do not care. You don't need a Archimedean scheme for central difference, or you can for whatever. But then in case also this single factor. So there's again 1 by epsilon fact on numeric expression or truncation area, and this only happens in density variable. So we're not in the other place if formula right. So that's what we need to do that. So that's then you do not worry about this damping. Okay. So and of course asymptotic-preserving. Let me just try to explain. Okay, a simple idea. So for this guy stuff, you're doing the explicit, implicit mixing formulation stuff. If both are stable, of course, put together stable. Just simple lemma. It just because this guy stable means its solution operator is bounded, and this stable means the solution operator bounded. Put it together means it's combined operator together, of course, bounded. So the method is unconditional stable. So it's stable. It's no problem pricing. And also the resolved issues on this stiffness, larger numerical area by this the method. Of course, you can use higher order method, but I try to just explain the idea. So this n plus means implicit. This explicit.
That's implicit. What is usually called semi-implicit.
Oh, I just did semi-implicit, yeah. So, what's good name? Half or?
Sorry, I didn't see that.
Yeah. Okay. So let me just try to see how to do this hyperbolic decomposition. So, again, I regard this mainly try to look at the equation itself instead of it's more part of look at the equation than actually do numerical computation. So you just look at the equation itself and borrow something. Okay, so here's a borrow. Okay. So I guess so here is the sort of the this blue part I mean slow dynamic, and red part is the fast dynamic. So instead of this introduce my parameter, unfortunately we have to introduce some parameter. How to determine best parameter we still do not know, but there's a parameter here. I choose sort of the so some flux here and 1 minus here. So now this guy itself is hyperbolic, and it's very easy to verify. Okay, and then this part itself is just what I say, just a wave operator, and then this is the stiff, but it's constant coefficients. So okay, I put even details here. So this is a good hyperbolic decomposition, and I now want to show you numerically it's indeed good. Okay, so I guess some details I probably just skip. Okay, just the usual one. Okay, so just okay, so just doing the simplest possible. This part is a flux splitting method. You just flux splitting by positive part, positive argument moving forward, backward, and doing this Archimedean usual one. And it's very simple. We can have the muscle scheme, but it's easy to explain, and it's just to sometimes I heard deliver that. That's the implicit part. So that's the calculation you have. It's very to solve numerically. Okay, so then so, if you look at this equation itself, you see how much truncation area is any truncation area on this part. You just look at the equation. It looks kind of all coupled together, but you actually put again density satisfies again always reduce nonlinear wave operator, and then have larger area will be produced by this is any density variable. Okay, so then it's also nice when doing actual computational, I guess for incompressible best method, I would got a starting point is called max skin or stagger gradient. And indeed, this part, if you take a limit itself, you have an incompressible limit perform a numerical setting and satisfy also same almost like a max skin besides continuous equation sort of mixing short stanza, long stanza, but it's almost like a max skin. So that's a numerical skin good. Okay. It's complication obviously with boundary, I don't want to talk about it. And when debugger, some part obviously missing not clear, so but it works perfectly fine. So I just doing this guy. So let me just work on a little more tricky part. So anything with fully the 3 equation with energy equation is become complicated. So then you require more thinking to do the formulation. Now here here's sort of the I put the Scott part out, just this scaled one, the pressure is scaled by 1 epsilon in the outer component. And let's just try to see how to do that, the hyperbolic decomposition. Okay, here's the here you go. Okay, so so this is you take this energy, have a stiff part out and non-stiff part out. So it's just usual as the polytropic gas, and also pressure also split by out, and then just do usual trick here. And then this is the blue one again is non-linear but hyperbolic. Then its linear part itself it's stiff, but is constant coefficient with speed 0 plus minus c squared by epsilon is alpha. So its formula is incompressible. So it works fine. And okay, so let me just show some numerics which Jeff have the conduct. And I probably just go a little bit quick on what basically we try to say this all speed. Verify the method itself robust automatically. If you low marker, you can complete low marker. High marker, you can complete high marker. Just automatically in the building the scheme. So that's what he was doing, checking through the large, the older one like a usual shock capture scheme. Then you also you're doing the small number low marker, and also how to always practical what to choose alpha, which we still do not have good idea, not a perfect idea. Okay. All right, I guess the first one is epsilon. Okay, now this epsilon is a marker number, is order 1 for shock for this shock problem, reflection waves, and it works fine to me. And maybe if somebody more picky, you say, okay, is some of not quite okay, but okay, and 2 points on the shock, it's okay, it's fine for me, but okay, you can't be picky. Of course, when I was student at UCA, Yang was my instructor, then all science mathematics blocking. And with Stan also we say, okay, look counting how many points in transition, okay, 1 or 2. Okay, I want to emphasize here. Okay, so it's okay, Stan also here, everywhere, of course. It's okay, so it's doing this kind of strong shock waves. You have the large one. I think it will be okay. So it's quite a difficult test problem. It works fine. So basically, I try to give you one more large. Usually, the skin cell building here, of course, more costing. We have to solve 1% equation, but that's you want to be automatic, then you have to pay it off. Okay, but this works. Just ignore on the person solver, but it works fine. Okay, so here is the sort of Lux Liu. It's Shudong Liu, the other Liu. Okay, by the way, you know what's population on Liu in China? Probably as size as the French people. Same last name. So, yeah. So let's just leave myself. And I just learned the numerics done by Jeff. So okay, somehow, but it works okay. Okay, so now what he tried to say is so check numeric errors. Actually, how much error you have for small epsilon, large epsilon. I think what he tried to say here. Oh, okay, so marvelous Degang Tang. She's not here. Okay, so the numerics which they use the follow idea from Degang and calculation periodic solution and see the lower marker and higher marker and see the skin self how much errors you have. I assume it's good because I cannot read. 10 to minus 3 or dependent resolution. So the uniformly have the uniformly have the 10 to minus. Yeah, it's uniformly consistent with epsilon. Basically, what Jeff wants to say. Okay, so that's the other example, which is Corolla. Also, of course, all the ideas on the flows come from Corolla, and he also did some calculation for simple water bubble in the example. I will not say much because I really quite complete follow exactly. Okay, step flow for incompressible region have Mach number small, and it looks so. This mainly we try to see the location is good and it's the right location. So I guess I just take it out. Okay. All right. So let me just move on now. Finally, get to kinetic equation. Okay. I still have some half hour. I'm able to explain some idea I learned from Pierre de Gang. Okay. So for computational purpose, it's sometimes quite different from analysis. And so redundancy is good. I hear the workshop by Dan. Redundancy can sometimes be good. So what I can say here, so we solve the equation itself. I just use simplest possible Boltzmann equation with the BGK. So this is the BGK, and solve this equation extremely expensive. What do we know? And on top of this, I add even more expensive. Not only solve Boltzmann equation, I solve also Euler equation. So it's coupled the redundancy equation. So it's always doing this kind of a problem. I will show you for the problems that you do redundancy to two set of equation, and one equation to the slow dynamic, one to the fast dynamic. Itself, but some of we play with, some ignore some part, which will gain some efficiency. Because if you really think about the complexity, this is over dominant this movement. So add some small epsilon is okay. So that's the idea. So okay. So now first formulate what's the physical understanding on the problem itself. So what we know up to signal moments and Gaussian distribution, and we know it's just giving the fluid behavior, Euler equation. So that's what we have. So I want to pick up the signal moments. So if we take up high order statistics, then it gives a sort of frustration, which is you give like a Linus tensor. So you put this Boltzmann in here and see sort of difference between the molecular speed and the background speed. Then you have the sort of the tensor here, different tensor here, and this even zero tensor here, and contribution to the conductivity, and also the tensor, Linus tensor here is a contributor, basically sort of kind of called upscaling, downscaling. So you have dynamic of the Euler equation, and with upscaling from contribution, sort of high order moments, high order statistics contribution from the kinetic equation to add sort of dissipation over there. At the same time, the motion dynamic of the motion of this this because this is not global Maxwellian. So dynamic of this Euler equation will give you the motion of the perturbation. So let me try to explain this over redundancy. So what is conclude about and how we can use it. Okay, so this is coupled the hydrodynamic equation, and it could be useful. Let me I have some example. So reactive localization, synchronization. Okay, I just remove difference. Okay, I just object here. Let me just be more concrete. So this is a work with Pierre and Luke. So what I say this guy itself. So this just reformation instead of like an S variable, like a G variable, sort of try to do localization. And zero, that would be like how to use as much zero as possible. So you write down this F distribution, the Maxwellian plus epsilon, mean plus G, sort of high order statistics. So this guy carries the zero moments on zero up to first signal moments. So it's any kind of high order moments. Okay, so write down the equation itself again. The previous equation itself write down in this more sort of upscaling, downscaling form. So this is the Euler equation. I choose this capital U means all the fluid moment variable, and this is the flux, and this is the contribution G. Now this only comes from G high order statistics here, and this sort of upscaling from the frustration to go to the continuous variable. And but then the motion of this dynamic of this guy is the global variable itself also gives contribution how to push the frustration move. So that's downscale. So that's our equation. But now this is overcomplicated, and you're not doing anything.
What is MU and what is the
Oh yeah, I'm sorry. Yes, I have to. So this is U is the fluid variable, M is Maxwellian, and this is the projection. You just take the projection to the fluid moment. I don't know what's good notation. I should have to explain the notation. I have more longer slides, but I sort of maybe just try to explain idea to ignore some of the details. Okay, so it's just some projection to the into the high moments. You take away the leading moments out.
and in LG what are the math
Which?
in that operator LG?
Oh, this is linear. I think this I probably explain. Let me just try to say. I should be more careful. So L is a linearized collision operator on this background. So you have the quadratic term, right? I have not interested. So basically, let me just see the two. Maybe it's blackboard. Sorry, I have to explain. So you have this, maybe I like here. So Q m plus epsilon g m plus epsilon g itself will equal to 2 epsilon Q n g plus epsilon square Q g g, right? And this we call the L g usual. Okay, so linearized along the background, that's Maxwellian. Okay, yeah, I should be more careful on my slides. Okay, so basically, but okay, I just try to say here. So now, so that's just a reformulation, the redundancy and morphin. So now here's sort of good things called how to localize. And localize usually have difficulty because scattering between the boundaries. So I try to say if as long as it's good cutoff, we will find. So you choose the H between 0, 1, and the fluid region is 0, and the kinetic part of 1 you want to pick up contribution by kinetic region. But you should take a transition in the fluid region to into AP. So that's quite crucial. So because when in the fluid region means the mean free path is small, and you have to do whatever you like. So, but it's sort of near close bounding. So now then G will sort of put you put G and 1 minus the decomposition fluid kinetic part, fluid part, and you just simply slow G fluid part is 0 because in the kinetic part this 0 and outside is 0, so it's always 0. So you can just simply ignore it. So that means this kind of equation G frustration itself you only need solved locally nearby the regime where you need it. And in front here have the here front have HK. So these are really localized. So really locally regionally can solve this equation. So now this is called a localized decomposition. And it's a numeric trick, of course. It's quite an efficiency gain is how small this region will be. Okay, so I guess some numerics, BGK, I guess so some effective Newton's number, and this idea also works for the sort of for the diffusion scale, which is I can say more details because
The salt test.
Yes.
That's a strictly hydrodynamic problem, right?
Yeah, I had two scaling. I had hydrodynamic scale and also the now. Okay, so the problem is that the problem comes from it can be the same test case for the Boltzmann equation, right? Relaxation. It just anything that in the transition itself is a non-equilibrium, so it's no longer valid for this problem itself happens to be very close to the for fluid equation. So yeah, you raise a good question. So we had some tests like for really important here shows up this important for kinetic factor for Mach number must be bigger than 2 or 3 something. Then it's important. Otherwise, Mach number below this 2 or 3 in practice is no contribution for kinetic part. So I know this question, but I just we do have the test more carefully. Say large Mach number, which is then the kinetic profile and the fluid profile completely differently. And indeed, then you choose more advantage. But I will try to instead of expand careful on the numerical behavior, I will try to explain how we formulate the problem. Yes, yes, you're certainly right. The kinetic effects in the non-equilibrium region is boundary layer or shock layer, and only when Mach number becomes large, like 2.5 or something, then there's a bigger difference. Otherwise, it's close. Yes. Yeah, that's certainly true. Yeah, I should use different example. So this is the radioactive heat transfer, and you just doing the sort of for the calculation. I will give you explain more details. That's why I have not written an equation, but I want to explain. So here sort of for calculations the kinetic model, which give good behavior, and this sort of localized kinetic model, like a micro-local, and also give good behavior. Also cannot see difference. And this one is the fluid model, of course, get a complete nonsense because it's not supposed to be true. That's equilibrium states for this radioactive transfer. All right. So let me just say a little bit more. So how understanding from numerical point of view. see the problems. If from pick up example a neutron transport equation. Okay, because Jose's paper here, and it's a lot of people work on this contributed subject. I just probably just make a small point of view, which from numerical analysis. Let me just explain. Okay, so the neutron transport I got more general. So the physics are really simple. Just you have dilute small particle hitting on the fixed large particle itself. You are scattering line of linear and tumbling. So more random work. And so you not follow this dynamic, fast dynamic, really for the slow dynamic, human scale. So this basically is a sort of jumping person process for long tumbling for this one. So transport equation right down the distribution. So that's in the time scale you have, and this can be assumption, absorption, and it can be source. And this the collision operator to describe how scattering behavior, long tumbling, how they change. Can be uniform or can be different, depending on medium itself. Okay, so it sets enough property on symmetrical and positivity, and also this coefficient itself is has sort of the positivity. So that's general equation, and this is a problem on the S2 because this on the assumption of small particle hit on bigger particle never change the momentum, never change the speed. So or you can use the example. Probably I will got more useful. I play with Alex on this bacteria how to move along, and this linear tumbling is more close to the rather than this equation. Of course, in this region itself, with random walk is close to Brownian motion, which is diffusion equation. That's how diffusion approximation come in. Okay, here let me write down, explain a little bit. Okay, so this is I divide by epsilon, doesn't matter. So it's so this is so random walk with jumping process. This is linear transport equation, and at the limit of this guy, because from the Brownian motion, it's like given by heat equation, and this must be close enough. Okay, so the way to work on this one, let me just do in one-dimensional, try to explain more clearly. So this V is like sort of cosine x in the angles. So from -1 to 1, actually it's a little bit easy to work with scattering, and it choose this sort of average, use this variable. It's average of the distribution and density. And now again, also redundancy. So write down this equation itself in the two parts. One more fluid dynamic and also frustration. G is like the frustration, density plus frustration. Okay, so nice about this linear problem is so easy to write down projection. So this is sort of that G is sort of higher order, any contribution to the higher order of statistics is have projection out of this part. Okay, so this is equivalent formula for this guy, and this will give you good dynamics. And we'd like to see indeed as epsilon go to 0, formally just say immediately from here, you will see this guy is exactly diffusion behavior. And then this part gives you how to do good numerics because projection properly. Okay. Yeah, so let's set up problem. So it's fairly elementary. So you solve this equation itself. So what it does here is again implicit explicit issues. So you from the higher moments itself here, G, you're solving this whatever because it's high hyperbolic, the dynamic follows. You just follow the simply Apollinean scheme. Just I just positive V and negative V, just Apollinean downwind, and then is projection. Important is projection. That's very important. So you have here is that you introduce a numerical area. 1 over epsilon is a larger numerical area, but projected. It's only in the moments, in the it's not in linear moments. So this kind of large area does not matter. Okay, so you can introduce a larger numerical area as you like, even 1 over epsilon is okay. So this just solve this equation because okay, we have a contribution to solve this integral equation is not too bad. And you solve this equation, solve this guy. Now you solve G here. Once you have G plugging here, you solve density. So this this implicitly can be explicitly realized because from this equation I have realized from G and plug in and solve this guy. Okay. All right. So I'm going to say 1 over factor of truncation area. We call it numerical distribution because it's a good sign and it's projected. Okay. So formally, epsilon goes below, you get the diffusion equation. I will explain how to prove.
But this is you have the stability condition of the.
Oh, to the next one. Yeah, yes, that's exactly. Yeah. The whole punchline is what is stability? Yeah, how we do that? Yeah, exactly. Okay, here's a sort of with Luke, and so it says skin is a uniform assuming source is 0, and then Sn is a sort of minimum scattering and sigma these coefficients, and under this CFA number, important here probability is plus. That means this is large. If epsilon small, I mean this guy. If epsilon large, I mean this guy. So this is less than to be plus. Okay, so that's the CF on this condition, then this is stable numerical scheme. And let me just digest a little bit. It's almost like the best constant you can have. So you choose a simple, like you choose this scattering coefficient like constant in this case, and then this guy CFA number even more pronounced. So dt times stepping is a delta x squared divided by 9 kappa. Of course, factor is a little bit over than the factor. This one. So if the epsilon small and slow with this guy out, you will restrict by the diffusion CFA number. And then, of course, we will be missing some factor here. Okay. And then for the epsilon large, this dominant, and this will be like a CFA number.
But this is not completely satisfactory because in the case, the diffusion case, you would like to use a kind of implicit scheme for the heat equation.
Oh yeah, that's right. Yes, that's right. Yeah, that's right. Yeah, exactly. Yeah, that's right. Yeah, I will try to play with it, cannot get it. Yeah, Yang always give the sort of key point. Yeah, no, yeah. So then this kind of now it can formation scheme is no problem, and it solve itself. You can just put it implicit, it doesn't matter. Anything is you just make it implicit. It's okay. You can do it. Anything is itself is the issue is that is then it's no longer have this implicit experience. You have to couple together. Then you have the low modes and high modes and couple together. It's extremely expensive. I would like to say that this is the more this is the most work I have done. As this part I want to like explicit. If of course I take it implicit, of course then I can realize, but then it's extremely expensive, which we don't like to have. Yeah. So I don't know. Maybe some of the smarter way to partially do something, maybe even higher order expansion, something, some way to control. Certainly is maybe practical workable, maybe not ever proven, but something try to pick up, do something implicit, but not too expensive. Not like direct work on this local variable implicit, because it's too expensive. Yeah, go ahead.
But it's not so bad because it's
this
not
good.
coupled in the position direction. It's only coupled in the velocity direction, right?
Yeah, no. So this is not bad.
So
No, this is good. I said Yang will mention about making implicit in here. Then we get to the implicit diffusion condition. Then it will be expensive. Here, this is not expensive. Yeah. This is not expensive. It's just up to winning. The n, okay, it's no cost. Okay, yeah. Okay. All right, so and you can also, for the linear problem, you can do some error analysis. So, and indeed it will be epsilon go to larger, it's no contribution. So, epsilon goes to small, no contribution. So it's basically uniform in the accuracy. Let's see. I guess I'm done. Okay, so thank you.
So any more questions or comments?
when you write down the transport equation for neutron transport,
Yes.
you introduce a 1 over epsilon in,
Oh yeah.
in the transport
Yes.
part, and then the
Yes. Yeah. No, Yang probably have to really answer this question. Yeah.
there is one which has 1 over epsilon in the v dot grad, and
One over T, which one? Let me see.
it's not here. It's not in the slides.
Not in slides.
Next one maybe.
Next one.
Oh yeah, here.
Oh yeah. Same thing. I can divide by
You
epsilon.
introduced this.
I divide by epsilon. Oh, same. I just divide by epsilon. Diffusion time scale. Like we know this London work. It's
You just introduced the scale.
okay. Maybe Yang can answer. What's the best way to? And of course, the people always ask why this diffusion time scale? Why is epsilon in front? Okay. I sort of just look a longer time, right? Yeah. Maybe you can answer. Yeah.
You only need the important assumption is that the last two terms are small compared to
Yeah, no, of course, mathematically.
the rest is just rescaling of x and t. So,
Yeah. Yeah. Yeah.
I have
course.
a very stupid question.
No, no, no.
Because I don't know anything about this asymptotic-preserving. So
Yeah.
my question is, if I take a scheme, a standard scheme that works well for that problem,
Yes. But work well mean in small
work well
epsilon.
work well in the following way. So I have some numerical computation for epsilon equal to 1, and then I make epsilon go to 0.
Yeah.
And I get the expected result, what I will get for the problem with epsilon 0.
Yeah. Well, the question is that
But that is not going to be asymptotic preserved.
no, it's may or may not depend on problem. So what I say here is if epsilon go to 0, if h fixed, then it's asymptotic preserving. If h had to be also small, then it's not asymptotic preserving. Yeah, because if epsilon go to 0, h even go to fast, then it's much more expensive. If you want to resolve in details, it's always come valid. But then it's not in here.
Uniform in X.
Uniform in epsilon, that's what keywords here.
Okay.
Yeah, yeah.
But as long as you have a method that is uniform in epsilon, you don't need to do all
No, not uniform in h, uniform in epsilon.
Okay, uniform in epsilon. And
Yeah.
you don't need to do all these asymptotic absorption.
Oh, no, that is fine. That basically, if you uniform in epsilon, basically, I trust it, you have to do this. If you do that asymptotic, it will be valid. I trust it, yeah. But that's the key part is uniform in epsilon, not only stability, also accuracy. And this accuracy, uniform stability, is not valid for all the variables, only variable for leading variable. It's not true. I'm definitely sure this is not in this fluctuation variable. So only variable true for this leading moments, leading variable. So the consistent will be much more careful. So only consistent for up to the leading variable, not for this g in here or some densities here. Yeah, so that's what this is what I thought. Yeah, so what consistent, uniform consistent leading is only for the leading variable.